So in this session, we'll talk about value at risk, the process of backtesting value at risk, and review the various VAR methods. So value at risk is defined as the maximum amount of loss over a given time horizon with a low pre-specified probability that the actual loss will exceed that value. We'll understand with an example. So if the 99% one-day VAR is equal to $100, what this implies is that in 100 random days or in any 100 days, there will be one day in which the loss will be greater than and equal to $100, and in 99 out of the 100 days the loss will be less than $100. If the 90% one-day VAR was equal to $58, for example, then what this implies is that in 90 out of 100 days, the loss will be less than $58, and in 10 out of 100 days, the loss will be greater than or equal to $58. So that's the definition of value at risk. Please note, it is specified over a given time horizon. For example, in this case it is a one-day VAR, and it is always specified with a probability. So there has to be a 99% one-day VAR, or a 90% 10-day VAR, or a 96% 100-day VAR. So VAR always is defined within a time period and with a pre-specified probability. Similarly, had I defined 99% 10-day VAR as equal to $100, what this means is that if I take 100 different 10-day periods, so basically over a span of 1000 days, and those 1000 days are been broken up into 100 10-day periods, then in 99 out of those 100 10-day periods, the cumulative loss or the total loss will be less than $100, and in one 10-day period, the total loss will be greater than or equal to $100. Similarly, had I defined a 99% yearly VAR, then in 1 out of 100 years, the loss will exceed the VAR number. So that was just a revision of the definition of VAR, or the value at risk. We will now understand the process of backtesting. Now let's assume that the 95% one-day VAR was equal to $100. Then in a period of 200 days, how many exceptions should we see? An exception is defined as any loss that is worse than the VAR. Since it's a 95% one-day VAR, in 200 days, 5% of the times we will see the VAR getting exceeded. So 5% of 200 is 10 days. That is, in 200 days, approximately 10 days the VAR or the loss should be higher than the VAR estimate, otherwise my VAR calculation is incorrect. So backtesting compares the daily VAR forecast with the realized profit and loss the next day. If the actual loss is worse, then the event is recorded as an exception. The risk manager then counts the number of exceptions over a window with t observations. So in our example, t is equal to 200. So in 200 days that we checked, we were expecting to see 10 exceptions or 10 exceedances. However, is it a guarantee that we will exactly see 10 exceedances? It's possible that we see 9 also. It's possible that we see 10 also. Or we see 11, 12, 13, any number. If the question is asked that in 200 days, what is the probability that you see 8 exceptions? That is exactly 8 exceedances. That is exactly 8 exceedances. Then how will we calculate this probability? So we can apply the binomial theorem, because please note that we are doing 200 trials. Each day, each trial can either be an exception or not an exception. So there is only 2 possible outcomes. The probability of it being an exception is 5%. So the probability of success is 5%. And the probability of it not being an exception, that is not exceeding the VAR, is 1 minus p, that is 95%. So in 200 different trials where the probability of success, the probability of seeing an exception in each trial is 5%, what is the probability of seeing exactly x successes or exactly x exceptions? It will be ncx p to the power x 1 minus p to the power n minus x. Please recall the binomial distribution and the binomial probabilities from part 1. So if we have a window of 200 observations, then the probability of seeing exactly 8 exceptions will be calculated as 200C8. P, 5% is the probability of an exception in any one trial. So 0.05 to the power eight and 0.95 to the power 200 minus 8, that is 192. So we need 192 failures and only 8 successes, that is exactly 8 exceptions. By the same formula, we can calculate the probability of exactly 3 exceptions, exactly 5 exceptions, exactly 10 exceptions also we can calculate. So in 200 trials, or if I collect loss data over 200 days, the probability of seeing exactly 10 exceptions can similarly be calculated as ncx p to the power x 1 minus p to the power n minus x, because the probability of seeing an exception in any one trial is again 5%, since it's a 95% VAR, so 5% chance that the loss will exceed the VAR. And the probability of seeing no exception, that is loss being less than the VAR, is 95%. So the probability of seeing exactly 10 exceptions in 200 days can be calculated as 200C10 probability of success or probability of an exception in any one trial to the power x, that is 10, 1 minus the probability of success, that is the probability of failure, to the power n minus x, that is 190. Please note that in this example, this will be the highest probability because the expected number of exceptions is also 10. So in 200 days, 5% of the times the VAR is expected to be exceeded. So 10 days, we would expect the VAR would be exceeded. The probability of exactly 10 exceptions can be calculated like this, and this will be a relatively higher probability as compared to 8 exceptions or 12 exceptions or 20 exceptions. We'll understand it again, and we'll understand the application of the concept of backtesting. But just to revise, the probability of exactly x exceptions is given as ncx p to the power x 1 minus p to the power t minus x. So what is the probability of observing exactly 0 exceptions out of a sample of 250 observations when the true probability is 1%? Or it is a 99% VAR. So the probability of an exception is 1%. It will be given as 250 C0 probability of success to the power 0, probability of failure, that is 0.99, to the power t minus x, that is 250 minus 0, or 250, which comes out to be 8.1%. So there's an 8.1% chance that in a year normally has approximately 250 trading days, we will see 0 exception. Now let's try to understand how this concept is used in our applications or used in validating the VAR. So let's say there is 250 days of data and it's a 99% VAR that we are estimating. So in 1 year, how many exceptions are expected? Please note it's a daily VAR. That will be 1% into 250, that is 2.5. Now let's assume that actually we see 20 exceptions. In such a case, should we reject our model? Saying that our model appears incorrect or our VAR is incorrect, because with a 99% VAR, if it was calculated correctly, we should have seen only about 2 to 3 exceptions or 2.5 exceptions. So if we see 20 exceedances, then probably the model is incorrect. If we see about 3 exceptions, then will we reject the VAR or will we reject our estimate? No, because now it looks in line. We were expecting 2.5 and actually 3 exceptions happened, so our model looks more or less correct. So this is the next step of the analysis that we will do. That is, we will calculate the VAR first with one sample of data, and then we will test it on another sample and see is the VAR calculation correct. That is, are the exceptions in line with our expectations? And if not, are they really high enough or low enough for us to reject the VAR model, or are they in line within acceptable limits? So let's do a few questions. Based on a 90% confidence level, how many exceptions in backtesting a VAR would be expected over a 250-day trading year? So if it's a 90% confidence interval, then 10% of the times we can expect the VAR to be exceeded, or 10% into 250, that is 25 days out of 250 we expect the VAR to get exceeded. A large international bank has a trading book whose size depends on the opportunities perceived by its traders. The market risk manager estimates the one-day VAR at 95% confidence level to be $50 million. You are asked to evaluate how good a job the manager is doing in estimating the one-day VAR. Which of the following would be the most convincing evidence that the manager is doing a poor job, assuming that losses are identical and independently distributed? So the VAR is 50 million and it is a 95% VAR. So all options have 250 days. So in 250 days, how many exceedances do we expect? It will be 250 into 0.05, that is 7.5 days. So if there are 8 exceptions, that's fine. That looks like a correct model. Over the past 250 days, the largest loss is $500 million. Please note, VAR tells us nothing about the largest loss. Over the past 250 days, the mean loss is $60 million. Again, VAR tells us nothing about the mean loss or the largest loss. It just tells us that 95% of the times the loss will be greater than 50. Rather, 95% of the times the loss will be less than 50, and 5% of the times the loss will be greater than 50 in one day. Apart from that, the one day 95% VAR tells us nothing about the average loss over and above the VAR. If over 250 days there is no exception, that is, there are 0 exceedances, then this definitely is an indication that we are underestimating or overestimating the VAR. So this would indicate that we are overestimating our VAR number, because in 250 days the VAR has never gotten exceeded, and if it was a 95% VAR, it should have gotten exceeded in 7.5 days out of 250. So D definitely indicates that this is not a correct model and the VAR is being overestimated because it is not getting exceeded even once. Now my apologies, is not 7.5 days, it will be 12.5 days. The explanation still remains the same. 8 is still closer to 12.5. 0 is the farthest away from 12.5. So amongst the options, D is the most convincing argument. So we'll now try to answer the question that what number of exceedances are acceptable and when should we actually reject our model. So when T is large, or the number of days is large, we can use the central limit theorem and approximate that the binomial distribution will be like a normal distribution. So for large samples, the binomial distribution does tend to the normal distribution. That is, we can take help of the Z statistic and do a hypothesis test to check if the number of exceedances is statistically different from the expected number of exceedances. So the expected number of exceedances is given as P into T. That will be our hypothesized value. X will be our actual observed exceedances. The null hypothesis is that the observed exceedances or observed exceptions are equal to P into T, that is the expected number of exceptions. And the alternative hypothesis is that the observed exceptions are different from the expected number of exceptions. If we reject the null, if we reject the hypothesis that X is equal to P into T, then we will imply that the observed number of exceedances is statistically different from the expected number, hence the model should be rejected. In other words, if this value of X is too different from P into T or the expected exceedances, that means our model is incorrect and we may need to recalculate the VAR. Please note, the Z statistic is calculated as the observed value minus the hypothesized value divided by the standard error. The standard error in the case of a binomial distribution or the standard deviation can be calculated as square root of NPQ, where P is the probability of success, Q is the probability of failure. So that will be the square root of NP into 1 minus P. So for example, the Z value for observing 8 exceptions in the previous example, wherein we had 250 trials and a 99% VAR. So the expected number of exceedances is 2.5. The observed exceedances is 8. So 8 minus 2.5 upon square root of NPQ, that is 250, into 0.01 into 0.99, that is P into 1 minus P, which comes out to be 1.573, will be 3.5. So the observed value of the Z statistic comes out to be 3.5. And with a 99% confidence, or 99% of the times for a two-tailed test, this value should be within minus 2.58 and plus 2.58. If it is greater than 2.58, that is, it is a value of 3.5, then we can reject the null that X is equal to 2.5, or we will conclude that it is significantly different from 2.5 and the model should be rejected. If it was within the range, then with 99% confidence we could not have rejected our model. For example, if we actually saw just 4 exceedances, so the Z value would have come out to be 4 minus 2.5 divided by 1.53, approximately equal to 1. If Z comes out to be 1, then with a 99% confidence can we reject the null? To reject the null, the critical value has to be either greater than, or the observed value of the Z statistic has to be greater than 2.58 or less than minus 2.58. So if it is 1, then we cannot with 99% confidence say that the model is wrong, or we cannot reject this null. So 4 exceedances are likely even though, or they can happen even if the model is correct. 8 exceedances are unlikely if the model was actually correct. So this is the same hypothesis test that we did at level 1. we'll understand a little more about the hypothesis test. So with 250 observations and a 99% confidence level, or a level of significance of 1%, we calculated that the probability of seeing 0 exceptions is 8.1%. That is 250 see 0, 0.01 to the power 0, 0.99 to the power 250. Similarly, we can see the probability of getting exactly 1 exception, the probability of getting 2 exceptions, this will be 250 C2, 0.01 to the power 2, 0.99 to the power 248. This probability comes out to be 25.74%. So what is the probability of seeing less than or equal to 2 exceptions? That is, you see either 2 or 1 or 0. So the cumulative probability of seeing less than or equal to 2 exceptions is 54.32%. And that is what the third column suggests or tells us. The probability of seeing 4 exceptions similarly is 13.41%. The probability of seeing 7 exceptions is only about 1%. So the probability that we will see less than or equal to 7 observations, or rather 7 exceptions, is 99.6%. So if, for example, we see 2 exceptions in the model. So in this model where expected number is 2.5, we in some particular case see exactly 2 exceptions and we reject the model. If we do that, then what is the probability that we are making a type 1 error? Type 1 error is the probability of rejecting a correct model. So we saw only 2 exceptions and we rejected the model. In such a case, there is a 71.42% chance that we are making a mistake, or we shouldn't have rejected. There's only a 30% chance that we are doing the right thing. Because 30% of the times there are 1 or less exceptions. If we see 7 exceptions and we reject the model, then 98.63% of the times we see less than 6 exceptions. So if we see 7 exceptions, should we reject the model or not? We would likely reject the model, but it's still possible that we have made a mistake, that it's just this sample that 7 exceedances have come. In another sample, it's possible that only 2.5 or 2 or 3 exceptions come. But the probability of that happening, or the probability of making a type 1 error, that is rejecting a correct model, will be very, very low. It will only be 1.37%. So if we reject the model with 6 exceptions, then there is only a 4% chance that we have made a mistake. If we see 10 exceptions, then we should definitely reject the model, because with 2.5 expected, 10 is a very large number. 99.98% of the times, if the model would have been correct, we would have seen less than 10 exceptions, or rather less than or equal to 9 exceptions. So there's only a 0.03% chance that we are making a mistake. So that is for us to decide that how much confidence we want to have. If we want to be really sure, then with even 4 or 5 exceptions, we will reject the model and recalculate. If we want to be very lenient, or we think that it's not a very critical application, then we can say, okay, with 6 or 7 exceptions, I will reject the model. 2.5 is expected. If exceptions are greater than 6, then we will reject the model, because 98.63% of the times there are less than or equal to 6 exceptions. So there's only a 1.37% chance that I'm making an error, or a 99.6% chance that I'm doing the right thing. So that's how we apply the hypothesis test. We compute the Z value, and then we decide whether we should reject the model or should we fail to reject the model. However, if we stretch this value too much, let's say even with 8 exceptions, I am not rejecting the model, then I may very likely commit a type 2 error. That is, not rejecting a model that is false. With 8 exceptions, should we have rejected the model? Yes, but if we are not, then it's quite likely we are committing a type 2 error, that is, not rejecting an incorrect model. So we have to decide that is, balance the probabilities of these 2 errors and keep a limit. So we'll study next what Basel says about backtesting and what is the limits that they have decided to adopt. So Basel says that in a 250-day 99% VAR, in the backtesting, if you see 0 to 4 exceptions, that means your model is pretty much correct, and there will be no potential increase in K. So K is a risk factor that Basel brings in. We will study it in more detail when we study Basel rules. For now, just note that they don't increase the risk factor. So 0 to 4 means the model is correct. If you see 5 to 9 exceedances, then Basel starts getting worried, because it's probable that your VAR calculation is not correct. That's why you're seeing so many exceedances. So in such a case, your risk matrix will be increased a little, and you will have to keep higher capital because your model may not be correct. So there will be some increase in K depending on how many exceedances you see. So you'll be in the yellow range. If you see greater than equal to 10 exceptions, then there will be a 1 unit increase in K, that is the risk measure, and you will be in the red zone, that is, your VAR definitely looks like it is incorrect. So if there are 0 exceptions also, the VAR may be incorrect, but that's not a problem. It just means that you have overestimated the VAR. So overestimating the VAR is a relatively lesser problem from a risk perspective as compared to underestimating the VAR. If you're in the yellow or red, that means you're probably underestimating the VAR and you need to recalculate the VAR. So there are two things about the backtesting process that you need to be careful about. First, backtesting only counts the frequency of the exceptions and not the extent. So if the loss exceeds the VAR, that is an exception. If it exceeds by $100 or by $10 million, backtesting doesn't care about that. So if it's $100 exceedance, it's not as big an issue as when it is a $10 million exception. So make sure that you have some other measure, some stress testing or worst case analysis that you're doing, so that somewhere the extent also gets captured. Backtesting will only count the frequency. And secondly, you should be concerned if there is bunching up in the exceptions. So in the 250 days, if the 8 exceptions are all coming on 8 simultaneous days, then again that will be a cause of concern, or you should be bothered, because that means that loss within a week's time can be really high, because if there are 5, 6, 7 continuous exceptions happening. So let's do a few questions now. Which of the following procedures is essential in validating the VAR estimates? Stress testing, scenario analysis, backtesting, or once approved by regulators, no further validation is required. No, we must do backtesting to validate our VAR calculation. And preferably, this should now be done on independent sets of 100 days or 200 days and see if the number of exceedances are in line with expectations. The market risk amendment to the Basel Capital Accord defines the yellow zone as the following range of exceptions out of 250 observations. So if there are 5 to 9, then it's a medium risk situation and it is in the yellow zone according to the Basel committee. Backtesting routinely compares daily profits and losses with model generated risk measures to gauge the quality and accuracy of their risk measurement. In 1996, Market Risk Amendment describes the backtesting framework that is to accompany the internal model's capital requirement. We'll study this when we study Basel. This backtesting framework involves the size of outliers. Please note, backtesting doesn't worry about the size of the outliers. It worries about the number of outliers. And that's how it tries to validate the VAR. So size doesn't matter. The use of risk measure calibrated to a 1-day holding period, that is correct, because we use the 1 year, that is the 250-day 1-day VAR with a 99% confidence level. The size of outliers for a risk measure calibrated to a 10-day holding period, that's incorrect. So the Basel requirement is that within 250 days the number of exceptions should be in the range of 0 to 4 for a 1-day 99% VAR. And it focuses on the number of outliers, not the size. So options 2 and 4 are correct. Tycoon Bank announced that there were 8 days in the previous year for which losses exceeded the daily 99% VAR. As a result, concerns emerged about the accuracy of the VAR implementation. Assuming that there are 250 days in the year, which of the following statements is or are correct? So in 250 days, we expect 2.5 exceptions. Actually, there were 8 exceptions. So option 1 is that using a two-tailed 99% confidence level, the current VAR implementation understates the actual risk in the bank's portfolio. The statement is correct because there should have been 2.5 and there are actually 8. So risk is being understated. Using a 99% confidence, the current VAR implementation overstates the actual risk. That is incorrect. The bank's exception rates for VAR may be inaccurate if the bank's portfolio changes incorporate the returns from low risk but highly profitable intraday market making activities. If there are a lot of market making activities that are happening and a lot of intraday trading happening, then there may be additional profit that may be coming in that is not being incorporated in our VAR, or that is not being incorporated in the exception data. So if the loss is greater than the VAR, then it will be an exception. So if the beginning value was, let's say, 100 and the ending value was 80, then there is a loss of 20%. And let's say this is higher than the VAR, so this will be calculated as an exception. So if we just use the end of day values, then our exceptions may be overestimated because total loss in the day was not minus 20%. There were some profits coming from market making activities and intraday trading that also should be added to this. So the loss actually was not minus 20, loss was only minus 10 after we incorporated these other returns also. If we just use the end of day portfolio values, probably it was an exception. But with the market making activities, probably this value was not an exception and this number of 8 may have been reduced. So the exception rates can be inaccurate if there are returns from low risk but highly profitable intraday market making activities, which is enhancing our returns. If these 8 exceptions all happened in the previous month, then the model should be re-examined for faulty assumptions and invalid parameters. That is correct. If exceptions are getting bunched up, then you should be particularly careful. So options 1, 3 and 4 are correct. So that was about the review on VAR and backtesting, an important review for the part 2 exam, highly testable. So again, make sure that you practice a lot of questions. Thanks a lot and see you next time.